In this video, we're talking about one particular type of probability distribution called the binomial. So in the beginning, I'm just going to talk about sort of the components of what makes something a binomial distribution or a binomial probability, and we'll look at some more advanced computations in the next video. But really the hardest part of these problems is sort of establishing what's what. The formulas themselves are pretty easy to compute. So in the binomial distribution, we're looking at some kind of procedure with n independent trials. So n is some fixed number, say 10 trials, and the trials are repetitions of some kind of process. So independence is an important piece here. We have to make sure that the trials or repetitions don't depend on one another probability-wise. And then in this procedure, each trial has to have two outcomes. One we'll call success and one we'll call failure. And we can decide what success and failure means, but there has to be exactly two outcomes. If there's more than two, or of course less than two, then this isn't a binomial probability. So for our success and failure, the probability of a success on any one of these trials is denoted by the lowercase p, and then the probability of failure is denoted by a lowercase q, although since success and failure are the only possibilities, q is always just going to be 1 minus p. And finally, what the binomial distribution actually looks at is the probability of x number of successes in the n trials. So x is our random variable in this case, so x is counting up how many successes show up in these n repeated trials. So as a simple example that you should keep in your mind, think of flipping a coin, say 10 times, and looking at how many heads there are. So 10 repetitions of this flipping, this 10 is our n, so there are 10 trials, one for each flip. A success in this case would be getting a heads, but you could also do this with success being getting a tails. It doesn't really matter, it just sort of alters your setup. Then p, our probability of success, well, the probability of heads on any given flip is 1/2, and then of course our q is 1/2 as well, since the probability of tails is also 1/2. And x here would be representing how many heads you got in the 10 flips. So this is just a really basic example of the binomial distribution, but it kind of helps to keep this in mind when you're looking at more complicated examples. So when we're actually looking at probabilities here, this is the formula that gives the probability of x. So again, x is our random variable. In that previous example, this would be the number of heads, and our formula says we're going to do a combination and choose x times our probability of success raised to the x power times our probability of failure raised to the n minus x power. This is the rest of the trials. So if we're flipping a coin 10 times and we wanted to know the probability of getting 3 heads, or we could write this as x equals 3, we can use this formula to compute this. So we would say our n here is 10, so 10 choose 3 if we want to get 3 heads or 3 successes. Our probability of success was 1/2 raised to the third. Our probability of failure is also 1/2. In general, these p and q don't have to be the same, they just are when we're flipping coins. And then the power on our q is 10 minus 3, or in this case 7. So we would compute this out, and this would be our probability. This one comes out to about 12% here. So here's a different example of a binomial probability problem. You didn't study at all for your ACT test, and you're just guessing randomly on all of them. Probably not a great idea. There are 20 questions that you're going to answer. Each one has 5 choices, and your score is based on the number of correct answers. So we want to evaluate if this actually is a binomial distribution. So we do have sort of repeated trials. With our 20 questions, we're going to be answering questions 20 times, which means that our n would be 20. And these trials are independent. If we are actually guessing randomly on each question, then the likelihood of getting each one right doesn't depend upon our other questions. In general, if you're taking a test, the probability of getting problems right are not independent, because getting one right means that you'd be more likely to get another right. So we've got repeated independent trials, and we only have two options here. We have success or failure. In this case, I would say that success was a correct answer, and then our failure would be an incorrect answer. You could also set up this problem having success be an incorrect answer and failure be a correct answer. Often you can flip-flop the two, but just in terms of the terminology, it makes a little more sense to say success is a correct answer. So if our success is a correct answer, we need the probability of success is P. Now there's 5 choices on each problem and only one correct answer, which means that the probability of success would be 1/5. And then our probability of failure is 1 minus 1/5, or in this case 5/5. So if our success is the correct answer, then X would be counting the number of correct answers. Just note that if you defined success to be an incorrect answer, these two probabilities would flip, and X would then be the number of incorrect answers. So you just have to make sure that whatever your success is, it matches whatever your P is and what X is counting. So then based on this, we could compute some probabilities. First here we have the probability of getting 12 correct, or in this case that would be the probability that X equals 12, right? Our number of correct answers is 12. So we could use our formula. N was 20, so this is 20 choose 12 times P, which was 1/5, raised to the X, which is 12, times our Q, or 4/5, raised to 20 minus 12, or 8. So our probability comes out to 0.000087, or this would be 0.01% approximately. So there's pretty low probability of getting exactly 12 answers correct. Next we have the probability of 20 correct, or the probability that X equals 20. This is the same kind of computation here, so we'll use the same formula and setup. Here's the probability that I get from my calculator. I left this in scientific notation because this is a very, very tiny number. Remember, 10 to the negative 14 power means we'd have to move the decimal place to the left 14 times, or there would be 13 zeros coming before the 1. This would definitely round to 0 under any of the rounding schemes that we're using in this class. But this is our probability for getting 20 correct. It shouldn't be too surprising that this is so small, because if you're guessing randomly on 20 questions, it would be nearly impossible to get them all correct that way. This third probability, we're looking at finding at least 18 correct. There's a number of ways to do this, and if you read in the textbook you'll see some methods using the calculator or other types of technology. I'm just going to do this sort of the most straightforward way using this formula we've got, but if you want to use a different method, that's definitely okay. So at least 18 correct means we could get 18 or 19 or 20 correct. So we really have kind of 3 possibilities here. So I'm going to look at the probability of each one of these, and because these are disjoint events, they can't happen at the same time, we can just add their probabilities. So here's our probability. Again, I'm leaving this in scientific notation because this is still a very small number, although it's quite a bit larger than the probability of just getting 20 correct. One more example to look at. Here we have a survey of 1,000 voters taken to see who they plan to vote for in the presidential election. So is this a binomial probability problem? Well, we have to have repeated trials that are independent. Now, repeated trials could be considered the survey of each one of the voters, so that condition is met. Now, the condition of independence, remember when we talked about sampling, when you take a survey of 1,000 voters, this is not with replacement. Because when you survey, unless it says otherwise, you're typically not going to be able to survey the same person more than once. Because there's not replacement, these are technically not independent. Because as we remove those who we've already surveyed, we're changing the population. However, if the population is large enough, this would be considered independent. So go back and look at the sampling video if you don't remember this. But it would probably be safe to say that we could treat this as independent. However, the problem here comes when we look at the results. The results of this survey are not going to be two options. If we're asking who people are going to vote for, there's more than two candidates in most presidential elections. So we'd have a problem there. Now, say we were interested in one particular candidate, we could consider success as voting for that candidate, and then failure would be a vote for anyone else. And this would be a way to turn this into a binomial problem. But as this is stated, we would say that this is not binomial. Here's a binomial probability problem for you to try, talking about overbooking flights for airlines. Make sure that this makes sense as a binomial probability to you, and you'll have to identify sort of what the components of our binomial process are before you compute the probability. That's it for this video. See you next time.